Okay, I think time is up. So let's start the first run for this morning. Your opponent.
Okay. I would like to challenge team double part 4 having magnets.
Problem number 4.
Number 4.
We'll start.
Accepted. Okay, problem accepted. Okay, now you have 5 minutes to prepare, and all teams, please write down the names of your representatives.把名字写一下吧。You want to continue? You want to start now? Or you need more time? You want to start now? Okay, let's proceed.
Hello everyone, my name is Wang Shenchao and I'm from stage3 and today the topic of my report is the number 4 climbing magnets. The problem statement. A tensile rod assembled from a cylindrical neodymium magnet horizontally to the vertical ferromagnetic rod, limiting the motion of the magnet to vertical direction. When the ferromagnetic rod is spun around its axis of symmetry, the magnetic rod begins to climb up. Explain this phenomenon and investigate how the rate of the climbing depends on the relevant parameters. And we will focus on the speed and the rate of the climbing. And there is a video, and in this video, you can see that in this video you can see that the magnets will rotate and it will climbing up. And a hypothesis. According to a dynamic, for a magnetic rod to climb up, there needs to be an outward force. And based on the system force diagram, it is evidence that the friction plays a crucial role in causing the magnetic rod to ascend. And this is our theory. And the static frictions. The friction force that prevents two surfaces from sliding past each other, and the kinetic sliding frictions. The frictional force that acts between moving surfaces. And in this picture, in showing picture, you can see that this process is the static frictions, and when it reaches maximum, and is the maximum of the static friction, and after it will go to the kinetic friction. In stage, a phenomenon where an object alternates between the sticking to a surface and sticking over it, and it will repeat again and again. And target. A measurement of the rotational force applied to an object causing it to rotate around an axis. And this formula will be an tau equal to r multiplied f multiplied the sin theta. And we define that r is the distance from the vacuum to the first contact point. And the f it means the force, and the theta will be an angle between the first and the lever arm. It's our experience setup, and we use a phone for recording and circulate magnets of different diameters, a drill and NG995 servo motors, an Arduino board, and an iron rod of different diameters. And this is our experience steps. First, we attach a magnet to an iron rod and insert the iron rod into a drill or a servo motor chuck and tighten it. And set up the phones and record the magnet's motions, and turn on the drill servo motor to make the magnet spin, and use the checker to analyze the rate of time in magnet. And this is our first variable. And we dependent variable is the diameter of the iron rod. And we control the vertical displacement in 4 centimeters and mass of the magnet in the 13 points as grams and neodymium magnets and angular velocities, and we use the two velocities, 2.4 and 3.5 rate per second. And we also observe the rate of the timing magnet. And this is our result. According to a diagram, we can see that we can observe that as the diameter of the iron rod increase, the rate of which magnets decline also increase, and they have a positive correlation. And the red line will be the 3.5 rate per second, and the blue line will be the 2.4 rate per second. And this is our second, and we change the mass of the magnets, and we also control the vertical displacement, diameter of iron rod, and neodymium magnets, and angular velocity, and the velocity will be 69 per point as rate. And we also observe the rate of the timing magnet. And this is our result. And we initially believe that the greater the mass, the lower the climbing speed, because it has a huge gravity. However, according to the experimental results during the graph, and we found that as the mass increase, the climbing speed will also increase, reaching its maximum at 13.8 grams. And beyond these points further, increasing the mass causes the speed to decrease. And these are the third variables. And we change the angular velocity of the iron rod. And we also control vertical displacement, mass, and the neodymium magnet and diameter of the iron rod. And we also observe the rate. And in this result, and based on the chart, we can infer that the faster the angular velocities of the iron rod, the faster of the climbing speed. And this is our difference rate of the angular velocity. And discussion. When the drill initially starts rotating, and the center of the magnet shifts away from its iron rod, and due to the rotation causing friction on the magnet. And in these two pictures you can compare, and you can see that the magnets have a clear, you can clearly observe that the magnet has a significant displacement. And from the perspective of static equilibrium, and when the magnet and the iron rod are initially at rest, and taking the contact point from the straight line down the middle of the end of the magnet, and the magnetic force and the normal force acting on the bottom and the magnets will be greater. than those acting on the top. And the MB is the normal force acting on the bottom and is the on the top. And the friction force at the bottom of the magnet is greater, initiating its rotation. And once the magnet is rotating, the friction force acts tangentially in the direction opposite to rotation, result in the upward vertical component that contribute to the climbing motion. And we have a shown picture in the math. And recent research shows that the magnet's upward motion occurs because the vertical components of the friction force is the gravitational force acting on it. And this is our two showing pictures, and you can see this is the iron rod, and when you rotate, and because the MB is normal force on the bottom is greater than the normal force on the top, and so it will cause the magnet to rotate. And the FKB means the friction between the iron rod and the magnet, and the FKB is on the bottom and FKT is on the top. And these two vertical components will make the magnet to vertical to climbing up because it will bigger the gravity. And the discussion, and this is our the whole process of this phenomenon. And we have two parts, and the first part is on the rest to initially retain rotation. And initially, the magnet remains stationary, and when the surface target is applied, it overcomes the static friction's initial rotation. And this transition from static to kinetic friction over result in a certain drag as the magnet starts moving. And you can see that it is the initial, and when the iron rod is rotated, and you will cause the iron rod will give the magnets FIN, and that FIN it means the friction force between iron rod and the magnets, and the iron rods on the buttons and it will bigger than the iron rod and will be a FIN on the top. And it will cause two situations, and this will be what we are going to say. And continuous rotation, and as the magnet rotates, the friction force acts tangentially in the direction outside to its rotation. The vertical components of this friction force contribute to the magnet's upward movement, and the climbing speed is determined by the interaction between the applied torque and the outside friction force. And this will to this situation, and this one is the vertical components will cause the magnet to climb up, and this is the stage phenomenon. Because it will let the magnet to rotate and will not without the climb up. And this is our conclusion. With the larger diameter of the iron rod, the faster of the climbing speed, and then with the faster of the rotation speed of the iron rod, the faster the climbing rate of the magnet rod. And the third is the climbing speed will gradually increase until the mass of the magnet reaches 13.8 grams. And the climbing rate increase linearly with the angular velocity is in our third experiment. And the magnetic force and normal force acting on the bottom of the magnets will be greater than those acting on the top. So, and the vertical components with the frictions between the iron rod and the magnets, and these two vertical components of the friction will exceed the gravitation force and cause the magnet to upward motion. And this is, thank you for this.
Okay, the opponent, 2 minutes.
Thanks for recording. And so the first question, hypothesis, do you consider a magnetic force?
Yes, we have considered magnetic force.
Okay. And so do you measure the friction coefficient between the rod and the magnets?
You
because you have to use your friction in your ear.
It means that
How big the coefficient is between the rod and the magnets. Okay, never mind. So is the magnet just turn it up or just go up straight?
it will rotate and it will turn it around.
And during this process, the friction, you just use the friction about the kinetic friction and static friction, right?
Yep.
And what kind of friction when it first up?
Okay, so and it will be a kinetic friction.
Okay. And so, do you have any theory to prove that you said climbing rate is linear?
About the angular velocity.
About your result, because it seems that your result is all linear.
And it is according to its proof.
How do you fit this? Because how do you get the lump?
We calculate
So you use the data to analyze.
Yeah.
Okay, I got it. And so you think about stage3 phenomenon. You have measured it, right?
Yeah, I have.
And tell me why it will cause stage3. In shortly, yeah.
Because when the iron rotates and it will cause the magnet also will cause the magnet rotate and it will not
The magnet will just spin up.
the magnet will not climb up and we have a video but it's not sure.
Okay, so then 3 minutes to prepare. Opponent.
Okay, Harriet and the opponent from Team Berlin, and today I'm going to oppose problem 4 typing magnets. For a problem statement, attach a rod assembled from cylindrical neodymium magnets corresponding to a vertical ferromantic rod. Limit the motion of magnets to a vertical direction. And when a ferromantic rod is spun around its axis of symmetry, the magnetic rod begins to climb up. Explain this phenomenon and investigate how the rate of climbing depends on relevant parameters. So here's a summary of a report about theory and explanation that the reporter used. He used a force analysis to talk about static friction and kinetic friction, and also these two different frictions transfer, and also use a stage3 phenomenon to describe how the magnet actually rotate up, and also so the reason I'm coming is about rotation. I also use a magnet, and also use a servo motor and iron rod to do experiment. And also about parameters, we use a different diameter of iron rod with 3 different diameter of rod, and also change the mass of the magnets, and also change the angular velocity of the motor to see there's a different results between these different parameters. And results shows that when a diameter position will increase to a velocity, and also when the mass is at 13.8 grams, you will have a biggest climbing rate. And also the proportional to the climbing velocity is about angular velocity. About the strength of report, I have seen the reporter have used some simple graphics to show how exactly the magnet rotate up. I think it's a very important point to show us how clear it is. Also has some connections between the torque and also how turn on speed, and use the friction coefficient to also I talk about different regimes to talk about how exactly the magnet happens, the stage3 phenomenon, and about the kinetic and static friction relationship. And for suggestion for reporter, I think reporter could have some more explanation about how exactly the torque affect on the magnets, and also also about friction, how it actually works weight and different force relationship. And also a reporter is suggesting to show better graph, because some graph of axis is not very clear, so I can't quite understand what the reporter is talking about. So I think reporter could show it in a better way, and also could explain the detailed axis about the graph. Also lack of error bar, because in our data that shows it just have some dots in here. So I mean the reporter could put some error bar in here and you see the difference. And about some linear phase, I think the reporter could tell more about why he used the linear phase to connect this data, and about why he used the linear phase, and about the difference between this data and the experiments. And some pages there are too much word like a conclusion, so I think maybe the reporter can shorten the pages more. And next about discussion with opponent, with reporter next I will divide it into 3 parts. The first part is about experimental discussion, and second part is about theoretical issue, and about last part is about data analysis. So I will invite the reporter for discussion. Okay, so can you show me your hypothesis page? Yeah, but in here you said, in the short question I asked you about, do you consider the magnetic force? Right.
Magnet.
Yeah, and you say yes, but can you tell me in here, do you use it in here? Or you just listen and you should draw it again on the blackboard?
You say draw the magnetic force.
Yeah.
And it will rotate, so the magnetic force will give the iron rod, and the iron rod will give the upside normal force.
So you mean the N is the normal force here?
Yeah.
And so you think it's from the magnetic force?
Actually.
From the direction I see because magnetic. Can I use the backboard?
Yes.
Because as the problem statement said, when you attach a magnet on the rod, so the magnet I think it will attract on this. Right.
Oh yeah.
Yeah, so I think the magnetic force maybe will be this way, so it can attract it. But the normal force that you show is this way. So can you tell me why or how the magnetic force will transfer into the normal speed?
It's positive.
Okay, we can do it exactly.
And it according to Newton's law of gravity, you will give it a velocity.
Yeah.
So the iron rod will be the force.
Also, you think that there's a different, just like a Newton's third law relationship?
Yeah.
Okay. And so can you tell me what's the effect that you use, the meaning of your normal force here? it's like, I mean, how the normal force works in the rotation of the spin of the magnets.
It means that the normal effect.
Yeah, how it affects.
Normal force will affect the magnet to be rotated.
Can you show it? How it rotates? Yeah, they are quite confused. Yeah.
When this iron rod, when the iron rod here,
Yeah.
and the contact I will go to displacement, and it will be the rotate here.
So you think that? So you mean that this is a magnet, right? And this is a rod. So I think there's a point that you will turn up. Yeah. And can you tell me is which points?
We have a picture that this is initial part, and when the iron rod rotates, the contact line will be here.
Can you tell me why it will change to this line?
Why this line?
Yeah.
Because the first contact line is here, and when the iron rod rotates, and it will be the contact lines will be here, and because project, and so it will go out and to
relocate.
rotate and
So you think the rod was being so like this will change and many rotates. Okay. I never know. Exactly. I go back. Okay, can you show me about your theory page? Yeah, this page. Yes, a bit. So can you tell me how the static friction and kinetic friction works here? In the yes, I mean, are they all the same friction, same kind of friction, or there are key changes in the spinning process?
Yes, it will change from the static to the kinetic.
In when? Yeah.
And first is in the magnets will into rotate.
So I mean when the rotate will turn to the kinetic friction. Yeah. Oh, yeah. I think that quite makes sense. Okay, so first, can you tell me about your setup page?
Setup page. Okay. This one.
Yeah. So here you use this things to do experiment. This to control angular velocity.
Yeah.
But in this instead you use the hand to push it, right? Or you have some automatic way to manually control the same angular velocity.
Angular velocity we also use the Arduino board, and we change its volts and to change its angular velocity.
Okay, so you use the Arduino to control it.
Yeah.
I think that's a very good way. And about that, you use a lure to be a blocker.
Yeah.
And so do you consider that maybe there's some friction between the magnet and the lure? Because it seems that in your video, the magnet will just slide around for the lure. So I think maybe will it affect the climbing rates?
We think it won't affect because the whole ruler is the same material, so I think it will be the same.
So in here's your control, right?
Yeah.
Oh, okay. Okay, can you show me your experiment, variable one? Yeah. In here you use the diameter of the iron rod. Yeah. And your result shows that the bigger. The bigger one can have bigger climbing velocity. So can you try to explain why you have the positive relationship?
Positive.
Why the iron rod with a bigger diameter will also have bigger climbing speed?
Because it has iron rod have big diameters, and it will displace us more big, and
You mean you will move bigger?
yeah.
So your turns out bigger.
Yeah.
So I think maybe you could show some video in here.
Okay.
But I think your answer I think it quite makes sense. Okay, about the most important point is not you're on top line. So do you have any theory to prove it's just a linear relationship, or how do you fit it? Do you use a linear here?
Yeah.
But you have used a street out. So you think that the street points or the street different diameter of iron rod is enough to prove it's a linear relationship?
We do a lot. We collect a lot of data, and we calculate
how many times do you do the for each experiment?
Do each per.
Yeah.
So we also do it 4 times.
Okay. Yeah. So I think maybe you change more different diameter of iron rod, like 4 and 5 and 1. So you maybe could more better to prove more diameter. Yeah. Okay. And for round 2, with the weights, I just said that the magnet, you have considered magnetic force in your force hypothesis.
Yeah.
But in here you change the mass on magnet, so you just apply another magnet or you just add something else on it. You change the mass on the magnet in here.
Yes.
Can I ask how do you change it?
We control its diameters and we also give it more magnetic.
But do you think that maybe will affect the magnetic force between the magnets?
Maybe it will, but I think it is not very.
Okay, I think maybe you can consider it next time. Okay, and about the results, we're up to results. Yeah, so can you tell me why it's not like a linear, it will become like a curve in here?
Oh no, because this when we reach a certain point at grants and it was and the vertical components is bigger than the edges, and when we go increase the length, and it will the gap between the gravities and the vertical components will be small.
Okay. In here, you also use a gravity for you have drawn the force here. This should just prove that is the mass of the magnet in your theory.
Yeah.
You also draw this tune line. I'm very quite confused. Is that this one is longer, but this one is shorter? So can you tell me what this tune line means?
Oh, this time is the normal force. The normal force on the average bottom and the top.
What? So this means bigger. The normal force.
The normal force on the bottom will be bigger.
Can you tell me why it will be bigger than top?
Because the gravities will cause the magnet to pull away the top, and it will put
Like a
the
much
bottom in and more against the
like much bigger pressure in here.
yeah.
But when you in your result you should you use more mass on stream, why the timing speed is much slower, because in your aspect you say that the gravity will pull it down. But if I think that maybe with the more magnets, maybe the effect of pulling down maybe will become better. But why the velocity will become smaller according to your results?
Because it is vertex version, and the vertical components will not large gap in with the gravity.
So you think maybe there's a critical mass in here, like when your mouse is like 12 or 16 have the biggest velocity. Like in here it will have the biggest velocity. Yeah, you think there's a limit range in here. Yeah. Okay, I got it. So can you show me the variable tree?
Okay, wrap this up.
Okay, and after having a discussion with the reporter, actually about mechanism about how the magnet actually rotate up, and the reporter said it's due to the kinetic friction and the static friction changing, and also actually about how the normal force works in here. So also the reporter also do some experiment to prove the different normal force, and about the weights, actually about why the different weights with not is a bigger weight, they will have bigger velocity, and the reporter said they will have a gap in here, so maybe there's a limit range in the mass of the magnet. And also actually about how you get the linear line here. And the reporter says it do very lot of times, but I think maybe you have to do more different parameters, like 4 centimeters and 6 centimeters to prove the linear assumption. And also I think the reporter also gives a lot of great explanation about how the magnet exactly rotate up. I think maybe you could put some more more some things to say what force is this, and this is all my conclusion.
Reviewer?
The reviewer, I want to ask some questions to the reporter and the opponent first. In your experiments, the magnets are climbing not the same, not the same speed, right? Because it will change, the friction will change by kinetic and static friction.
You say the rotate and the speed,
The rotate speed.
climbing speed
Yes,
will not
be the same because
yeah.
how do you define the rate of
The rest, the magnet,
climbing rate?
we use the we use a phone to record and use a tracker to check, and we also control the dispenser in frozen, so we can.
How do you define the climbing rate of the magnet?
I think the reporter used the climbing velocity is the climbing rate of my definition.
Why do you think the velocity is linear to the angular velocity of the ball?
Because we collect a lot of data and to calculate.
I think maybe it's not linear, but according to the reporter's data, it shows like linear.
Okay. What do you think the main factor is the main factor of the climbing of the magnets? And
The main factor, and
what the main force?
the main force that is to climb up, and we think it is the vertical component.
I think it's a gravity force that the landing to spin it up.
Okay. Do you think the friction of the ruler is an important factor?
We think it will maybe it will not affect, but because our ruler is also give us that version, so I think it's
What do you think?
I think it won't affect the friction between iPhone and iPhone.
Why do you think the mass affect the in your experiment?
why I do the math.
Why do you think it affects?
The method because it have a big the greater gravity.
What do you think?
Because I said gravity force is the most important force. Because when the mass will pull it magnet down, so the down particles have bigger moment force, maybe it will turn off.
Do you when you are changing the mass, do you change the length of the magnet?
Yeah.
Do you think the magnetic force of the magnet and the rod is great parameter? Is important parameter? The magnetic force is an important.
Yeah.
2 minutes for the reviewer to prepare.
everyone. I'm the reviewer from Numerical. First is a summary of the report. The report shows their experimentals and tools, and it used the stick-slip motion as their theory. And then in first experiment, they do the different rod diameter and find out that bigger diameter has bigger speed. And then it's the second, the mass of the magnet. They found out that it has a maximum velocity happens. And then the third experiment, they do the angular velocity of the rod, and they found out the climbing rate is proportional to the angular velocity. And then is the discussion of their theory discussion. They think that the torque of the friction and the magnet and the gravity force is the main factor to the effect. And then is the overall of the report. They have some good things that they do 3 parameters and they have clear photos to explain. But they have less graphs and their theory are not quantitative. And they only shows the experiment tools, but didn't show the setup. And they have lack of data that they only use 3 data points on their diameter experiment. And then as the opponent, there are some good things that their time managements are good, and they have some good suggestions about the experiment, and they use a blackboard to demonstrate. But they didn't investigate questions further. And then is their key discussion. First, the opponent asked why the large diameter costs faster, and the reporter said that the large diameter causes shift more. And then the second asked why different mass have different magnetic force, and the reporter said that it is because the torque of the torque and of the torque. And then they talk about the the report thing is because the torque of the magnet of gravity should be balanced with the friction torque of the magnet, so the Maxwell effect. And then is our question. First question is our we asked that how to define the climbing rate, and the reporter said that they use phone to calculate, and the opponent agreed with it. But we think that because the climbing rate aren't same during the climbing, so they have to define a small, like when it is the same, it remains the same, and it can be the climbing rate. And we asked why it is linear, and the linear to the angular velocity of the rod. And the reporter said that it's due to their data, and the opponent said that it's not linear, and we agree with the opponent that it might be approximate but not linear. And we asked what's the main factor. The reporter said that it is the torque. And
time is up. Reporter, 1 minute.
Okay, this is our concluding remark, and thanks for our opponent. Thanks for your opponent's discussions. Thank you for opponent's discussions on the transverse version, and we will find an easier way to clarify and reduce the testing size and the video showcase. And we also have prepared the video, but you have a needs error. And when the mass variable, we don't consider the magnetic force on the extra mass. And thanks for the suggestions. And also we think the curve lines on the diagrams. And for reviewer, we think the main feature of the timing rate is a vertical component of the function, and we will put the original database on the PowerPoint. And for discuss about the timing rate, and we define the timing rate because we control the displacements in the 4 centimeters, and we use the phone to record the displacement, and then we go to the tracker and we track the rate, and because the displacement is also the same, and so we can use this to calculate to show the timing rate. Okay, that's my reading.
Thank you. Now, questions from the viewers?
I just want to clarify that. You think the magnet, does it climb up or it rotate and climb up? Does it rotate with
Yeah. How does it climb up? Does it
Yeah,
climb
yeah,
up
those
directly
videos.
or it rotates and then climb up?
Because the power statement still it needs to the vertical
The
climb up.
question
So
is,
the
how
question
does
is,
it
directly
climb up?
climb up or it rotate and climb up?
if not, it will rotate.
It rotate, right?
Yes.
So the question is, if it rotates, then in the FY plane, does the force balance in this plane?
And
The force acting on the magnet balance in this direction, in your force analysis for all of your three.
that is the
Yeah, balance in this direction. The net force is 0 or not.
Horizontal force, do they balance?
Why? And what is the extra force?
you said the
You can go back to the force analysis. Actually, how many forces are in this direction? You only go one force. That is the hands, right? Yes,
normal
but
force.
yes, but it only have a normal force, it will detach from that, right?
and it also has a magnetic.
So how do you think?
The, you said think of the
In this direction,
Horizontal.
horizontal,
like rotate like this.
yes, then how many forces?
How many force?
And how large are them?
How many force and
Yes, how large?
how large?
Yeah.
The magnetic force, the friction, and the gravity force, and the constraint.
Just the horizontal. Just the horizontal.
Horizontal, the magnetic force and the constraint force of the rod.
Technical.
The
Okay.
For horizontal is a magnetic force, and over force like a rod give it, and the blocker will give the magnetic force almost a force too.
So are these force balance?
No.
Okay.
we think because the normal force is here, so it has a friction on this direction. So it has another friction.
Okay. Thank you.
Yes, please.
So if you have an upward force, so is this the force constant? If it's constant, then you have a constant acceleration. But what you observe is it's climbing up with almost a constant speed. So what's the cause of it?
If your vertical force is constant, you expect constant acceleration. In your observation, you observe a constant speed.
Because it has also have a this and it will not kind of constantly.
Did you really see the slip state motion?
In our video, you can see that you have a certain move of the red points, and you will not climb. You will just in the original phase.
Do we have other questions?
Yes, I want to follow that force analysis. Hypothesis, yes. I always ask basic questions. So what is the main force contributing this climbing motion? Could reviewers, what do you think? The main force contributing this climbing motion?
We think it's the friction.
You think it's friction force? And how about opponent?
I think it's gravity.
Gravitational force. And
We
the
also see
opponent?
the friction.
You also think the friction force?
Okay. Okay.
Time.
This is for the reporter. 4, 7, 5, 6, 6. And the score for the opponent. 6, 7, 5, 6, 6. Score for the reviewer. 6, 6, 5, 6, 6. Okay, good. So it's the end of the session, and if I think the jurors can have some general comments if you want. Okay, no, that's fine. Yeah, if you have comments for them, you can give them comments later. Okay, thank you very much for the morning session.
Thank you.